Simple pendulum. Are you able to see the screen? Simple pendulum as part of oscillations. The diagram also I given. Are you able to see the screen? Yes or no?
Yes, sir.
Right. So first of all, what is simple pendulum? After that, for small oscillations, the oscillations of a simple pendulum will be SHM or not. We'll check, and then we'll see the time period of simple pendulum. Okay. First, what is simple pendulum? So a simple pendulum is a heavy point-sized mass. A simple pendulum, ideally, what you can say, a heavy point-sized mass. A heavy point-sized mass suspended by a massless string or in negligible mass string, massless string or a string with negligible mass. Okay, and in these conditions for that string is inextensible. The, that means string should not extend, and torsionless. Okay, then it is called an ideal simple pendulum. Ideal simple pendulum. I repeat once again, a heavy point-sized mass suspended by a massless, inextensible, and torsionless string is called ideal simple pendulum. Are you clear this point? Yes or no?
Yes, sir.
You can see the first diagram, a simple pendulum. This is a bob, let me say a sphere. A heavy sphere, mass is more, but size is small. That is the condition. Connected to a string or a wire of length L. Capital L is the length of the string, small l is the length of the pendulum. What is the difference between length of the pendulum and the length of the string means? A small difference. You can see here, small l is equal to capital L plus R radius. That means length of the pendulum means length of the wire connected to the bob plus radius. That means the length up to center of mass or center of gravity of the bob you need to consider. That is the length of the pendulum. Small m is length of the pendulum. Are you clear this? Small l, length of the pendulum. Whereas capital L is the length of the wire connected, string connected plus radius r. That is the difference. But in reality, how to define simple pendulum? In reality, that means heavy point size means we can't define point size. Then in reality, you can take a heavy metallic sphere. Heavy metallic sphere. Okay. Or a bob. That sphere you can call it as bob also. Heavy metallic sphere or a bob suspended from a lightweight string. Light string. That is the lightweight string. Okay. This is used as a simple pendulum. Are you clear this? Now I can see. Yes. The distance between point of suspension to the center of the bob is called length of the pendulum. Small l. What is small l? Length of the pendulum. How to define length of pendulum? Length of pendulum is equal to distance between point of suspension to CG of bob, center of gravity of bob or center of mass of the bob. Okay, you can see here up to this point, point O to the point of suspension, this point A. Okay, that is the length of the pendulum. That is defined with small l. If you want length of the wire, capital L plus radius also. Now we need to prove that for small oscillations, the simple pendulum oscillations also executing SHM. For that, you can see this diagram already. If it is oscillating from the mean position O to extreme position D. Are you clear this diagram? Yes or no? Are you able to see the diagram? Mean position O to extreme position D. This length L is the length of the, yes. So this makes an angle theta here. You can see here this angle theta from the mean position to the extreme position. Angular displacement is theta. Then you can see this is also theta. This angle also. Then this mg weight of the bob resolved into two components, mg cos theta, this component. Okay, along the length. This mg sin theta perpendicular to the 10. Mg sin theta. You can see a tension T acting along the length. Okay, then in equilibrium condition at extreme position, what is the equations? At extreme position, the bob is in equilibrium. So that you can observe here, tension T is balanced by mg cos theta. Are you clear this? So you can write tension T is balanced by mg cos theta. This is equation number 1. Okay. Next you can see here mg sin theta. Another force is there. This mg sin theta force is acting towards the main position. That is the restoring force. So restoring force is equal to mg sin theta. Okay. Actually here mg sin theta f is opposite to the angular displacement. Angular displacement is towards right. Mg sin theta is towards left. So f is equal to minus mg sin theta. Minus means f is the force opposite to the displacement of the bob. Okay, that is the meaning. F is equal to minus mg sin theta. Are you clear this? Where f is called restoring force, f restore is equal to minus mg sin theta, t is equal to mg cos theta. Okay, so you can see our angular displacement theta, length L, length of the simple pendulum. Let us say some x is the arc length. Yeah, this is the x arc length. Then what you can write theta is equal to arc length x by radius L. You can write like theta is equal to x by L. Yes or no? Then for small angular displacement, f is equal to minus mg sin theta. You can write for small angles, for small angular displacement. Sin theta approximately theta for small angles. Then you can write f is equal to minus mg theta. F is equal to minus mg theta from equation number 2. See, equation number 3 is theta is equal to arc by length, x by L. Then what you can write f restoring is equal to f r restoring minus mg into theta is x by L. That is equal to minus mg by L into x. Are you clear this? F is equal to minus mg by L into x. What does it mean? F restoring force is directly proportional to negative displacement x. Okay. Second to Newton's second law, suppose F restoring is equal to ma, where m is the mass of the bob. Where m is the mass of the bob. Then what you can write here? ma. Then you can write above equations these two. F restoring gold minus mgx by L na equation number 4 and equation number 5. From 4 and 5, mgx by L is equal to ma. Yes or no? Then what you can write? ma is equal to minus mgx by L. Then a cancel. Sorry, mm cancel. Then a equal to minus g by L into x. equation number 6. A equal to minus G by L into 6. G by L into X. G by L is some constant. Then from this what you can get, acceleration is directly proportional to negative displacement. The bob is oscillating, small oscillations, and its acceleration is directly proportional to negative displacement. From this what you can conclude, the oscillations of simple pendulum are SHM or not? If acceleration is directly proportional
Sir.
to negative displacement. Yes?
Sir.
Yes. So it is proved that for small oscillations, it is proved that acceleration is directly proportional to negative displacement for small oscillations. Okay. Then why small oscillations? Is the condition is that sine theta approximately theta. That's why small oscillations. Then in that case, for small oscillations, the simple pendulum executing SHM. Simple pendulum executing SHM. Are you clear this point? That means the oscillations for small oscillations, the oscillations of simple pendulum is a simple harmonic motion. Okay, right. So this is the proved. Next, time period of the simple harmonic motion. Time period. Time period T. How to calculate this time period? You can see our equation number 6. Acceleration A is equal to minus G by L into X. Okay. Now we have an equation. Acceleration A is equal to minus omega square X. I remember SHM. A equal to minus omega square Y or omega square X. Where Y means if oscillations are along Y axis, X means oscillations along X axis. That is the same convention. Along X or along Y, no problem. But linear simple harmonic motion. Then from these equations, equation number 6 and this equation, A equal to minus omega square X, you can equate minus omega square X is equal to minus G by L into X. Then X cancel, minus cancel. Then what you can write, omega square is equal to G by L. Where omega we said angular frequency or angular speed. That means so the omega angular speed of SHM is omega is equal to root G by L. Omega is equal to root G by L. That's the equation number 7. Then time period, what is the relation time period T and omega? We know that time period T is equal to
2 pi n.
No, 2 pi by omega. Remember 2 pi by
Sir.
omega. Now that is equal to 2 pi by root of G by L. 2 pi by root of G by L. Then the time period equation T is equal to 2 pi G by L, you can write upside. This L will go up, then 2 pi root L by G. Have you seen this equation? Time period of simple pendulum 2 pi root L by G. Yes?
Yes, sir.
Right. So this is about the proof of the simple pendulum time period. T is equal to 2 pi root L by G. Then what factors it depends? Time period is does not depends on the mass of the bob. Does not depends on the mass of the bob. Okay. That means it is independent of mass. Are you clear this? Does not depends on mass or shape or size of the bob. It is independent of mass, shape, size, etc. Depends only length of the simple pendulum and acceleration due to gravity at that place. That means T proportional to root L, T is inversely proportional to root G. Are you clear these points? Suppose if the G is constant for a given pendulum, if G is constant, Then I can write, that means for a given place G is constant, then T1 by T2 is equal to root of L1 by L2. For a same place G is constant, then the two pendulums you can take ratio of their time periods is directly ratio of their square root of their lengths. T1 by T2 is equal to L1 by L2. Okay. So this is about understanding about simple pendulum. Next applications of this you can see now. Seconds pendulum. Seconds pendulum. What is this seconds pendulum? Seconds pendulum means if the time period of a simple pendulum whose time period of oscillation equal to 2 seconds. A simple pendulum whose time period of oscillation t equal to 2 seconds. Are you clear this? A simple pendulum whose time period t equal to 2 seconds. Then that is called seconds pendulum. That means it is something like to and fro motion equal to 2 seconds. Okay. Yeah, total time period is 2 seconds. Yeah, 1 second for one swing. That's why you can say 2 seconds. Are you clear this? This is called seconds pendulum. Next, we know all the formula t equal to for seconds pendulum 2 pi root L by G. What is the length of the second pendulum? You can calculate. See here, t equal to 2 seconds, you can substitute 2 is equal to 2 pi root L by G. Okay, then 2 to cancel. Then 1 is equal to pi root L by G. Then what you can write? Then I want L value. Squaring on both sides, L is equal to, from this L is equal to G by pi square. Are you agree this? See here, 1 square is equal to pi square
Sir.
into L by G. Then from this, L is equal to G by pi square. G value you know, 9.8. And pi square is pi equal to 3.14. 3.14 whole square. 3.14 whole square is approximately 9.86. Approximately 9.86. 9.8 by 9.86. Okay, right. That is approximately 0.994. 0.994 meter. Approximately L is equal to 0.994 meter. 0.994 meter approximately equal to 1 meter. Approximately 1 meter. Are you clear this? So length of the seconds pendulum approximately equal to 1 meter. Okay, right. So this is the condition of seconds pendulum you have to understand. Okay, are you clear up to this? Right.
Sir.
Now she say graphical understanding, graphs between L and T square. We have a relation already. Time period T is equal to 2 pi root L by G. I can write T square is equal to 4 pi square L by G. Now the graph between L and T square. So how it is related? T square is equal to 4 pi square by G into L. So T square you can imagine Y, then Y is equal to some constant M. M into L is equal to some X, Y equal to Mx. So it is something like a straight line where Y is equal to T square, X is L. Then how the graph? You can take along X axis length of the pendulum, along Y axis T square. That is like a straight line. This is about T square L graph. Is a straight line with a slope M is equal to tan theta. So this tan theta value equal to 4 pi square into G. Are you clear this?
Yes, sir.
Right. So the time period we have drawn a graph where time period versus length t square L for this slope behavior. Next we can go for one more graph t versus L, time period versus length. Then in that case how it is related? T proportional to root L. For that what you can take? You can write like this. L is equal to L is equal to G by 4 pi square into T square. L is equal to G by 4 pi square into T square. Or T square is equal to 4 pi square into LG. Like this. This equation also can take. Then it is something like y square is equal to 4ax. What is this equation? Y square is equal to 4ax. Parabola. You remember? Parabola equation? Yes or no?
Yes, sir.
Then like t square is equal to 4 pi square g into L. Then in that case, if you draw time period versus length along x-axis, instead of t square, you can take time period t along y-axis. Then the parabola with respect to symmetry with respect to L, length, x-axis, is the t versus L, time period. Then this shows a parabolic graph. Okay. So this is about the next important graph, t versus L. In that case, we'll get a parabola, symmetry about length. Then you can mix these two graphs, straight line and parabola. It will come, there is intersection point, origin, and let us say some point P. What is this point? Where point P, t equal to t square now? In which case t equal to t square for point P? Anybody can guess? 1. Very good. For t equal to 1, this intersection point will get. Then in that case, what is the length of the pendulum? The intersection point P such that t equal to t square, such that what is the length? That means you can substitute that equation. T square is equal to 4 pi square by g into L for a given length of the graph. Length of the pendulum you can calculate. Where t square is 1. 1 is equal to 4 pi square by g into L. Pi square is we know 9.86. G we know 9.8. Then approximately those two cancel. Then L equal to 1 by 4 meter. That is 0.25 centimeter. 0.25 meter, that is equal to 25 centimeter. That is equal to 25 centimeter. That means this is an application. Point at which where the two graphs are intersect, that point time value is 1 second, and length of the pendulum for the given time value is 25 centimeters. Are you clear this application?
Yes, sir.
Right. Next we'll go one more application. Suppose we have a pendulum of length L1 and the time period is T1. Then in that case T1 is equal to 2 pi root L1 by G. Similarly, another pendulum of length L2, its time period is T2. Then time period T2 is equal to 2 pi root L2 by G. Now these two pendulums are connected back to back. Then new time period for a length of L1 plus L2 bob. For a length of L1 plus L2. That is T. Then what is the relation between T1 and T2 and T? Then what is T value for L1 plus L2? 2 pi root L1 plus L2 by G. Are you clear this? Then I want relation between, yes. How will pendulums connected means only single bob I'll keep same mass like this. This is the first pendulum. is the second pendulum of L1, L2 length. Then one bob I remove and another length I'll add. This length I'll add here like this. Only one bob. L1, L2. Are you clear this now?
Yes, sir.
Yes. Now, for this time period, how much? 2 pi root L1 plus L2 by G. Then what is the relation between T and T1 and T2? Then I can write here. We know L1 is equal to, from this equation, what is L1? L1 is equal to G by 4 pi square into T1 square. L1 is squaring on both sides. G by 4 pi square into T1 square. L2 is, last 10 minutes. L2 is equal to G by 4 pi square into T2 square. Are you agree this? From above equation I have written this,
Yes,
equation I have
sir.
written this. Then what is L1 plus L2? From third equation, L1 plus L2 is equal to G by 4 pi square into T square. Then these three equations you can compare. L1 plus L2 is G by 4 pi square T1 square, G by 4 pi square T2 square equal to G by 4 pi square T square. From this you can write, you can substitute L1, L2 value here. Left side G by 4 pi square into T1 square plus G by 4 pi square into T2 square is equal to G by 4 pi square into T square. Are you clear this? G by 4 pi square, G by 4 pi square cancel. Then you can write T1 square plus T2 square is equal to T square. Are you understood relation between T1 and T2 and T? If you can add the two pendulums, yes or no?
Yes, sir.
Right. Similarly, you can subtract also. That means if you remove the length L1 minus L2, then finally you can write T is equal to root of T1 square plus T2 square. Okay. So like this you can write, suppose the two pendulums length is subtracted. Then you can write T is equal to root of, what you can write, T1 square minus T2 square. Okay. Then effective length, then the time period is T is equal to root of T1 square minus T2 square. Right. Now, next application, if simple pendulum, if simple pendulum if simple pendulum keep inside a lift, non-inertial frame, what about the time period? Inside a lift, that is a non-inertial frame. Have you remember non-inertial frame model?
Sir.
Then what happened? Time period you can see inside a lift. So the lift is accelerating upwards like this. This is the lift. The top side is freely suspended like this. Lift is accelerating with acceleration A upwards. That is the new time period. The G dash will become what happened? G plus A. Then time period T dash is equal to 2 pi root L by G plus A. Then what happened? Time period decreasing or increasing?
Sir, decreasing.
Decreasing. Very good. Suppose if the lift is moving downwards with an acceleration A,
G
then
minus A.
minus A. T double dash is equal to 2 pi root L by G minus A. Very good. Suppose the lift is falling down with an acceleration A equal to G. Freely falling case.
0.
0. Sorry, time period not 0. You can see here. T dash
Sorry,
is
sir.
T double dash is equal to 2 pi root L by G minus A. That means L by G minus G. G minus G is 0. That means L by 0 is infinity. Then T double dash is infinity. What is meaning of infinity? Anybody can guess? What is the meaning of time period infinity? In the case of lift is falling down with an acceleration is equal to g. That is called freely falling lift. What you can say? Freely falling lift. Understood?
Yes, sir.
In the case of freely falling lift, time period infinity means there is no oscillation. There is no
Yes,
oscillation.
sir.
Infinite time it won't move. That is the meaning. Infinite time it won't move. There is no oscillation. Okay. So this is about the case with the acceleration due gravity g changing. Then in that case, how the time period of pendulum you can see. First case decreases, next case increases, and finally it is infinity. That means no movement of pendulum. In which cases this is applicable? Lift is freely falling, or you can take inside a satellite. Pendulum inside a satellite also same. Pendulum inside satellite. Inside satellite also I said, okay, A equal to G. Okay, so in that case also time period will be infinity. Or else where the G0, where G0, effectively freely falling lift inside a satellite, and there is a free space outside Earth. There also pendulum will not move. Okay, and at the center of the Earth, can you guess? At the center of Earth,
No movement.
no movement. At the center of Earth also G0. Center of Earth. Okay. See here, how many cases came where the time period is infinity? 4 cases. Freely falling lift, okay, or freely falling elevator, or inside a satellite, or a free space outside the Earth, or center of the Earth, where time period of the pendulum is infinity. That means no movement of the pendulum. Okay. So this is about the applications of time period of simple pendulum. Are you clear this? Next, if we go from on the
Yes, sir.
surface of Earth, if we go from equator to pole, what happened time period of simple pendulum? Equator to pole.
Sir, increases.
Here T is inversely proportional to root Z. Yes or no? Root Z. At equator, G value is minimum. Net pole,
Sir.
maximum. At pole, it is maximum. Yes or no?
Yes, sir.
So G is going from minimum to maximum. Then time period will going from maximum to minimum. So that means if you go from equator to pole, time period will be decreases comparatively equator. Are you clear this? Time
Yes,
period
sir.
will be decreases compared to equator. Okay, because G is slightly increasing from equator to pole. Similarly, pole to equator, reverse also you can say like that. So this is about variation of G with respect to time period of simple pendulum. Next, last one more case. If it is a non-inertial frame, a moving bus, a moving truck or moving bus, so you can suspend a simple pendulum like this. So this moving with an acceleration A. Are you clear this? Then what are the forces acting first? mg vertically down,
Um,
ma pseudo force acting opposite direction, ma pseudo force, ma. So
yes,
mg
sir.
and ma acting, you can see here like this. You can now simple pendulum you can draw separately for this mg like this, mu like this. Then what is the resultant acceleration? A dash is equal to root of a square plus g square. Root of a square plus g square. So the time period is t is equal to 2 pi root L by root of a square plus g square. Okay, this is about time period of simple pendulum in the case of moving bus. That is in the case of
Yes, sir.
non-inertial frame. Okay, so that's all. So this is about simple pendulum and time period calculation. Okay, motion of the simple pendulum showing a simple harmonic motion. Okay, so thank you one and all. So this is about the today's class. Have a nice day.